Hello everyone, today's mini lesson on related rates will be taught by myself and Ted Zhou. And so we'll be using derivatives to find a rate at which a quantity changes by relating that quantity to other quantities whose rates of change are known in the context of a word problem. And a rate of change is usually done with respect to time. Okay, let's look at our problem. So we have Lance, a budding astronomer, and he's looking through his telescope and he sees a planet in the distance. So after fiddling with the zoom function on his telescope, kind of just like with the camera, Lance has found that the circumference of the planet increases at a constant rate of 6 millimeters per second. Lance wants to find the rate of change in volume, which is in millimeters cubed per second, when the radius of the planet in his telescope is 15 millimeters. So that's the radius he sees in the telescope, not the actual size of the planet, obviously. Okay, so before we jump into the question, we need to first establish some variables. So our first one is that c is the circumference of the planet in millimeters. Second, we have that v is the volume of the planet, and the units for that will be millimeters cubed. And finally, we have that r is the radius of the planet, which is also going to be in millimeters. And so we can use these variables and plug them into formulas. So the first formula we have is that c, circumference, is equal to 2 pi r. The second one we'll need is the formula for volume. So v is equal to 4/3 pi r cubed. And we can relate that to the goals for our problem. So in the context of Lance and looking at the planet through his telescope. So given that the change in circumference, dc by dt, is equal to 6 millimeters per second, we can look and solve for dv by dt. So change in volume when the radius of the planet in his telescope is equal to 15 millimeters. And the units for the change in volume will be in millimeters cubed per second. Okay, so in order to work out the problem, we're going to need to break it into multiple steps. The first step will be to establish what you're given. So we're given that the formula for circumference is equal to 2 pi r, and that the change in circumference is equal to 6 millimeters per second. And based off of that, right there, we can take the derivative of both sides. So the derivative of c using implicit differentiation will be dc by dt, and 2 pi stays because it's a constant. And then by implicitly differentiating radius, we'll have dr by dt. Next, we're going to need to plug in the known value of change in circumference. So just plugging in our given value of dc by dt. And based on what we're given, we know that it's going to be 6 millimeters per second. After, we're going to want to solve for change in radius now that we have everything else figured out. And so by dividing both sides by 2 pi, we have that our change in radius is 3 pi in millimeters per second. Now we're moving on to the second part of the problem. So the first part was using circumference c equals 2 pi r to figure out our change in radius. And using the new givens, the formula for volume, knowing that change in radius is 3 over pi, and we're going to find that when the radius of the planet is 15 millimeters in Lance's telescope. And so again, we're going to need to take the derivative of both sides by using implicit differentiation. V becomes dv by dt. R cubed using the power rule becomes 3r squared dr by dt. And the 3's cancel out, so our final formula right there is going to be dv by dt is equal to 4 pi r squared times dr by dt. Our third step is going to be plugging in known values of change in radius and radius itself, so r and dr by dt. And here we see that r is equal to 15 millimeters, so we're going to plug that in right there. And we know that dr by dt is equal to 3 over pi millimeters per second, so we're going to plug that in right there. And finally, when we multiply everything together, we get that our value for change in volume is going to be equal to 2,700 millimeters cubed per second. Right there. Okay, so finally, we need to understand the answer in the context of our problem. So using our value of 2700, we can state that the volume of the planet is increasing at a rate of 2700 millimeters cubed per second when the radius of the planet appears to be 15 millimeters in the telescope. So here we can kind of use the picture. The big round oval in white, it represents what Lance sees through his telescope. And through the animation you saw just now, you saw that the planet increased in size. And so when the radius is equal to 15 millimeters, we see that using our calculations, we know that its volume is increasing at a rate of 2700 millimeters cubed per second. That's all. Thank you.